Because batteries operate under a current of electrons and ions migrating back and forth from the electrodes. This behavior, therefore, can be analyzed by measuring the resistance, or better, the impedance. Since impedance measurements are carried out at a series of frequencies, it also reflects time constants. And because several mechanisms in the battery are time dependent, it is possible to deconvolute these mechanisms by processes by impedance spectroscopy. So let us see how impedance spectroscopy, or better electrochemical impedance spectroscopy, EIS, can be used to analyze a battery system, such as a vanadium redox flow battery. The discharge reactions that occur in a vanadium redox flow battery are vanadium 2+ ions to vanadium 3+ ions. The electrons that are being released go from the positive electrode, where vanadium 5+ goes to vanadium 4+. But let us concentrate on the discharge at the negative electrode, where vanadium 2+ will be consumed and vanadium 3+ will be formed. The vanadium 2+ ions are in the bulk, and this concentration of ions is everywhere the same. The migration then is determined by ohmic behavior, also called drift. This is usually assigned as conductivity, indicated here with a K. Note that this mechanism is not time dependent. From the bulk, the ions migrate to the surface to donate the electrons. This happens through a layer where accumulation occurs of the species. The migration mechanism here is a process that is called diffusion, assigned by D, and is time dependent. This diffusion layer is known as the Guth-Chapman layer. Once the ions arrive at the surface, they absorb and donate the electrons. This is the electron transfer reaction and is assigned here as R0. The absorption layer is known as the Helmholtz layer. Then the new vanadium 3+ ions must leave the surface through the diffusion layer, going back into the bulk. This means we have split up the overall mechanism into conduction, diffusion and reaction rate, which happens at specific places in the battery. The reaction rate is also a time-dependent process. This kind of mechanisms also occur at the positive electrode and is very general for all kinds of electrodes in batteries. To recall, here we look at the spectrum measured on a circuit with a resistor, Rs, in series with a system of a resistor, Rp, in parallel with a capacitor, Cp. This last system is usually called an RC circuit. The spectrum then is a semicircle shifted from the origin. Here the resistor Rs is responsible for that shift, and the semicircle comes from the RC circuit. The final touchdown at low frequency on the right hand side is the overall resistance, hence Rs plus Rp. From the maximum of the semicircle, it is possible to calculate the capacity of the capacitor. Now, every RC circuit that will be placed in series will give us an extra semicircle. These semicircles are usually overlapping. Each of the RC circuits mimic a specific process, which is characteristic time, which can be analyzed by the frequency at the top of the semicircle. Now we can distinguish between the various phases in the system. In the bulk electrolyte, there is only migration according to ohmic behavior, because there is no concentration difference. This will give us the Re. In the Guth-Chapman layer, the ions are subject to a concentration difference and are thus diffusing, which leads to an RC circuit. Then, within the Helmholtz layer, the actual charge transfer takes place, which is also a time-dependent process. This too is reflected by an RC circuit. So we made a simple cell to measure the impedance by an impedance spectrometer. We took a screenshot of the impedance spectrum, and indeed we see such a typical impedance spectrum as predicted. Unfortunately, it is not always that simple. In the case of an electrode in a lithium-ion battery, usually an extra phase arises as a result of the reaction of the electrode with the electrolyte. This phase is known as the solid electrolyte interface, the SEI. This SEI introduces an extra diffusion process and thus an extra RC circuit. Besides, the ions and electrons needs to be inserted into the electrode material. This is also governed by diffusion. This means that the equivalent circuit needs to be further expanded with another RC circuit. It becomes even more complicated if we consider porous electrodes or electrodes fabricated by a coating of particles. This has direct complications on the Guy-Chapman layer, the Helmholtz layer and the diffusion profile in the electrode. Despite the complexity of an impedance spectrum, a good experimentalist will be able to completely convolute such a system and interpret the measured spectrum in understandable processes, hence going from a complex system to a complex plane, and vice versa.